that the terminal side of an angle makes with the x-axis. So if this is the angle, that we've moved from the positive x-axis, then the terminal side is this red line that you see, and the tip of that red line, or the terminal side, which is on the circle, on the unit circle, it's called the terminal point. But the angle that that terminal side makes with the x-axis is called the reference number. Okay, so that was then. But now we will talk about terminal side and reference angle. So there's a slight, I hope you catch this slight change in terminology. So this was then. This was then. Now we will look at we would like to know about reference angle, and terminal side. So compare these two terminologies with that, and there's a slight change. Okay, so let's first talk about the reference angle. What is it? We want to make sure that we fully understand that. So this is the acute angle. It is the very important acute angle. Do you remember from basic high school geometry what this is, acute angle? Well, acute angle is any angle which is less than 90 degrees any angle less than 90 degrees. So it is the acute angle. Let's call it theta r. Theta r. So reference angle. Theta for angle and r for reference. Theta r. That is formed by the I think I should draw a picture before I continue, so I'm going to do that right away. Something like that. So this would be x and y, like that. So let's say this is our angle, and we assume that we got here by going counterclockwise or in the positive direction to this. So, and this side is the terminal side. This red line is the terminal side, and the angle, the acute angle theta r, formed by the terminal side and the x-axis. So on this drawing, where do you think is the reference angle? Think about it for a few seconds before I draw it. It is the angle theta r defined by the terminal side and the x-axis. So if you pointed in this direction and you said this region, you're absolutely correct. So theta r. Okay, that's one thing you should know about reference angle. The other thing you should know is that reference angles are always positive. So let's write that down. So this is not reference number, right, which we learned earlier. This is reference angle. And the reference angle is always positive. So you could have, for example, to get to this terminal site or to get to this reference angle, we had to go, let's say, positive, say 210 degrees, right? Let's say. So 180 plus 30 degrees. So the reference angle would be 30. But if we got to this terminal side going in the clockwise direction, that means if we went 100, instead of going 210 degrees this side, if we went 150 degrees this side, it would be, the movement would be in the 100 minus 150 degrees, so it would be clockwise minus 150 degrees, but still, the reference angle theta r would be positive 30 degrees. But, so the negative angle can be the angle which we trace through to get to the terminal side. But the reference angle itself is always positive. Okay, so having said that, let's give some examples. So we want to find the reference angle for theta equals minus 210 degrees. Okay, this was just a coincidence when I said 210 degrees earlier. But anyway, this is good because this is negative 210 degrees. So it is in the clockwise direction. Right? Let me write that quickly. So, well, I'll write it here. So first, note that for theta, we need to move in the clockwise direction, right? Because of this negative. Okay, so let's draw this. A picture is always very helpful, right? As long as the picture is not too complicated. So this is x, and we have y. Like that. So we start with the positive x-axis side, and this is minus 210. So we're going this way, and the clockwise, and so up to this point is minus 180 degrees, or minus pi, and then add another 30 degrees in that direction, so we end up somewhere here. So our terminal side for this would be roughly in this region here. And so the minus 210 degrees is going like this, and this is minus, tracing minus 210 degrees angle. Okay, so they want us to find the reference angle. Well, the reference angle is the angle between the terminal side, which is this red line, and the x-axis, right? So theta r is that which they're asking about. Well, if we know from here to here is 180 degrees, then to get to minus 210, we have to go additional 30 degrees, right? And that'll be positive. So theta r is equal to 30 degrees. Okay. So let's do another one. Let's find for theta equals 135 degrees. This time, notice this is positive, so the movement is going to be in the counterclockwise direction. So first, note that theta, for theta, we need to move in the counterclockwise position. Or direction, sorry, counterclockwise direction. Right, because this is positive. All right, so let's draw this. So going counterclockwise, we know that from here to here is 90 degrees, and then add another 45 degrees to it, and we end up in the second quadrant, right? So it would be here at a 45-degree angle. This is where the terminal side is. And this angle degrees. And so what is the reference angle for this? Think about it. What would you think is the reference angle? So the reference angle is in this location. And we know that because this is 45, then this has to be 45, right? So the reference angle in this case is 45-degree angle. So let's see, let's do another one. I think I have one more example on this. Maybe let's say, maybe two more examples. Okay, so example, we want to find the reference angle for theta equals 810 degrees. Okay. Okay, so first notice that this is moving in the counterclockwise direction, right? Because it's positive. So movement is in the counterclockwise direction, like that. All right, so let's draw this. Let's see where we have to be with this angle. So this is to move this up so you can see it like that. Okay, so this is a large angle. So let's see. We know that one go around the in the positive direction is 360, right? So twice that, it will be 720 degrees. And when we get to 720 degrees, then another 90 degrees will get to this. and all of it in the counterclockwise position, direction. So here's one go is 360 degrees, another go counterclockwise, that's 720 degrees, another 90 degrees, we're here. So we are on the y-axis. That's where the terminal side is going to be. The terminal side of this positive 810 degrees is going to fall right along the positive y-axis. So we're here. And I will try to show how we ended up here. So we go, that's 360 degrees, right? Let's go one full round, that would be 720 degrees. And then we move, and there we have 810 degrees. So at this point, we are at 360 degrees. At this point, we are at 720 degrees, and at that point, we are at 810 degrees. Okay, so that's how we got there. So what is the difference? What is the reference angle then? Well, the reference angle is the positive angle between the terminal side and the x-axis, which is 90 degrees. So that would be theta r in this case would be, so that's theta r is equal to 90 degrees. Okay, let's do one more. Suppose we want to find the reference angle for 33 pi over 4. Okay, so once again, this is a very large angle, right? 33 pi over 4. So let's see if we can break this up to see how many revolutions around the unit circle would this be. So if we assume 32, so let's break this up. So to try to visualize which or in which quadrant this is, let's break it up. Right? So if we do 32 pi over 4, so we do 33 pi over 4 is equal to 32 pi over 4 plus pi over 4, right? That is equivalent to this. So 32 pi over 4, what is that? That is 8 pi, right? 8 pi. Several revolutions around the unit circle, plus pi over 4. So let's try to draw this. Like that, and so this is also positive, right? Positive 30. That means the movement is going to be in the counterclockwise position, and 8 pi. So we know that if we go one full circle around the unit circle, that's 2 pi, right? That's 2 pi. So far we went 2 pi. Let's go one full round around all these axes, so that'll be that. So that is how much? Where are we at right now? Do you know? We're at 4 pi, right? So we keep going. So go one more around here. So what is that? Do you know where we are now? If you said 6 pi, you are correct. And then let's continue. And we go there. So what is that? That is 8 pi, right? At 8 pi, we're right there on the x-axis. But that's not where we stop, right? We have plus pi over 4. Because that's 33 pi over 4. So we have to go another pi over 4. If you go pi over 4, you end up being in the first quadrant, right there, oops, like that. So that is the terminal side of that angle. And theta r is right there. The distance or the angle between the terminal side and the x-axis. So theta r, thus theta r is equal to pi over 4. And that you can read from that too. So, like that. Okay. So those were some examples. So now we want to take advantage of reference angles to calculate the value for the trigonometric functions for any angle. So we simply convert the angle to its reference angle, and then we find the trigonometric function for the original angle based on the reference angle. So let's do that. So basically that we were saying that if you take, say, the sine of 33 pi over 4, that's the same thing as if you take sine of pi over 4. That's why we are doing this, to convert this to this. Tangent of that is equal to tangent of this. Then why deal with this when we can deal with a much simpler angle measure like pi over 4? Okay, when we calculate trigonometric functions. So that's the idea. But of course, let me add, of course, that tells us the measure of the angle, but it doesn't say about the algebraic sign, right? The algebraic sign will depend on where the terminal side is. So that for these angles that we had before. So here, to calculate the value for, say, sine of negative 210 degrees, right? We can do, let's do that. Let's do that here on my calculator. So you can see it here. So if we take the sine of negative 210, so sine of minus 210, right? What is that value? It's 0.5, right? So if we take the sine of 30 degrees, so sine of 30 degrees, that is equal to 0.5. But here, notice that the sine in both, if I bring this back, the sine of any angle in the first and the second quadrant is going to be positive. So that's why even though minus 210, it's going to be in the second quadrant, the sine value is still going to be positive because that's what happens in the first and the second quadrant. The sines are positive. So the beauty of finding the reference angle for any awkward angle like this is that we can then find the trigonometric function value of that simpler reference angle, and that's equal to the same thing, cosine of this would be equal to cosine of minus 210. And we know we have the special table values for that, right? In this special value table, you don't see any angles for minus 210, right? But you do have a 30 degrees angle. So cosine of that, let's say, would be square root of 3 over 2. But of course, that's as far as the measure of the angle. But as far as the sine of this, we have to pay attention to which quadrant this is and what is the trigonometric function sine in that particular quadrant. Okay, for example, 135 degrees. So if the reference angle for 135 degrees is 45 degrees. So, and in this table, right, in this table, I don't have any 135 degrees angle. But I do have 45 degrees angle. So if I was asked to find what is the cosine of 135 degrees, if that was the question, instead of going with 135, I'll go with this table of special values. Cosine of 45 degrees, which is the reference angle for 135 degrees, which would be square root of 2 over 2. But not quite yet, right? Because square root of 2 over 2 is the quantity measure of that angle. But with cosine, with 135 degree angle, we're in the second quadrant, and we know that in the second quadrant, the cosine is in the second quadrant is negative. So if I punch this into the calculator, so if I had to write this down without a calculator, I would say the measure of cosine of 135 degrees is equal to minus square root of 2 over 2, right? But with a calculator, we can verify that. It's going to be some negative number. So let's say, so let me first do this. Minus of square root of 2 divided by 2, what do we get? Look at that. We get minus 0.707106 and so on, right? But now let's do it using these functions. Cosine of 135 degrees is minus 0.707106 and so on. You see that? So the reference angle is only going to help you figure out the measure of the original angle in an absolute value version of it. It's always going to be positive, but you know which quadrant the original, the terminal side is. Then, given this, remembering all of this, you can decide what sign the measure will have, whether it's going to be positive or negative. Okay. I hope it's clear why we're using the reference angle. So we're going to move forward with further descriptions of this. So let's see. To evaluate trigonometric functions for any angle, right? Any angle, not just these special values, right? Any angle. This is what we do. First, find the reference angle. For the original angle, like what we did, 135, negative 210, 810, so on. So first find the reference angle. Then second, determine the sine trigonometric function by noting the quadrant where the terminal side is. So determine by function by noting the quadrant where the terminal side is. That means where in this circle, which quadrant is the terminal side. Okay? So we find the reference angle, and then we note where the terminal side is in these quadrants. Okay, so let's do some examples. So we want to find the exact value of the following trigonometric functions, right? Okay, so for part A, we want to do that for cosine of minus 60 degrees. All right, so this is minus, so the movement is in which direction? If you said clockwise, you're absolutely correct. So we have that. And this. And then so minus 60 degrees would be somewhere here, like that. So this would be 60 degrees, and this is movement is in the clockwise direction, that way, 60 degrees. Okay, so the reference angle for this, which is the angle between the terminal side and the x-axis, is 60 degrees, right? It's positive 60 degrees, and we have a special table of values for that, and it's going to be in the fourth quadrant, right? So we make a note of that. Now, cosine of 60 degrees, cosine of 60 degrees is 1/2, right? So we know it's 1/2, but what is the sine of the cosine in the fourth quadrant? Well, if you have any doubts, cosine, remember, is equal to x, right? So in the fourth quadrant, cosine of x is equal to positive. Yes, because the x-axis in this quadrant is positive for first quadrant, and the fourth quadrant, the cosine is positive because that's where the positive x-axis is. Okay, so we have positive 1/2, like that. Okay, so for part B, let's calculate the tangent of 750 degrees. Right? So that's the question. Well, let's figure out where this is. So this is equal to, so 750 is equal to, if 360 degrees is 1 full revolution, or 2 pi, and add to that another 360 degrees, which is 720 degrees together, that would be another full revolution around the unit circle. So this we can write as 720 degrees plus 30 degrees, right? We can break this up into that. And this is 2 pi. This is 4 pi, sorry. This is 4 pi plus 30 degrees. Well, 4 pi would be 2 full revolutions around the axis. So let's draw that. So here I go with 720 degrees. So that's 360 degrees, right? Let me mark that. Then I'll continue. And I get to that point. That's another 360 degrees on top of this. So that's 720 degrees. But this is 750, so I need to go another 30 degrees. I'll end up in the first quadrant. So I'm just going to draw the 30-degree terminal side, which is at 30 degrees angle in the, so theta r. So that's the terminal side, and therefore the terminal, or theta r, is going to be equal to 30 degrees. It's the first quadrant, so the tangent of 30 degrees, we can look it up in the special table of values, but let's derive it, right? So tangent of 30 degrees is equal to sine of 30 degrees divided by cosine of 30 degrees, right? This sine of 30 degrees is 1/2, and cosine of 30 degrees is square root of 3 over 2, and so we end up with square root of 3 over 3 after simplifying, right? We get 1 over square root of 3, but we can't have a radical in the denominator. We have to rationalize it, so times square root of 3 over 3. So that's, and that's in the first quadrant, so this remains positive, where the tangent, sine, cosine, tangent, cotangent, secant, and cosecant, all 6 basic trigonometric functions are positive. So that's that. And so that is, well, this is, so that's that, yeah. Okay, so that's, well, this is the final answer. Sorry, I should have not boxed that. So this is what we were looking for, that one. Okay, so let's see another example. I hope you're seeing why reference angles are important. So C, we want to find cosine of negative 7 pi over 3. So that's the question, right? Okay, so let's see what this angle is. We can say, we can break this up. This is a large angle. To make it easier for us to know which quadrant this is, we know that, let's break this up to cosine of minus 6 pi over 3 plus minus pi over 3. Let's break it up like that. This would help because minus 6 pi over 3 is simply minus 2 pi. All right? So minus 2 pi minus plus minus pi over 3, right? Or minus pi over 3. It makes no difference. Like that. So this is, what's happening here is that we are moving clockwise all the way through this, right? So let's draw the picture. Okay, so we have minus 2 pi, so we want to know in which quadrant we're going to be once we go through this angle. So it's going to be minus 2 pi, that's going clockwise, like that. So that is minus 2 pi. So up to this point is minus 2 pi, up to that point. And then we keep going, right? Plus minus pi over 3 in the clockwise direction. So that's minus pi over 3 is just 60 degrees. So we end up with having the terminal side to be somewhere here in the fourth quadrant. So let me continue that. So come to here. And so the theta r is going to be minus pi over 3. Okay, just like what we have there. So this is cosine of that. Let me bring this down. So we were asked to find cosine of that. So instead of this, we can find the cosine of this. And well, sorry, no, this is going to be positive. So that was an error. Sorry about that. So reference angles are always positive. So, but it moved in the clockwise direction in the fourth quadrant when we did that, when we added negative pi over 3. Okay, so then instead of calculating cosine of that, we can simply calculate cosine of pi over 3, which would be 1/2, I presume, but here it is, the special table of values. So cosine of 60 degrees, or pi over 3, is 1/2, right? But it's in the fourth quadrant, so in the fourth quadrant, cosine values are positive, right? That's where this comes in handy. So in the fourth quadrant, cosine is positive because cosine is related to the x value in any quadrant. So like that. We'll get to that in more detail when we get to polar coordinates. So we have positive 1/2. So the answer is, where would I want to write this? So here, 1/2. Like that. Okay. So this would be that. Cosine of, so basically cosine of pi over 3 in fourth quadrant, which is what we have here. Okay, so in addition to the trigonometric formulas we've learned so far, I'm talking about sine of x is equal to y over hypotenuse, or opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is sine over cosine. Cotangent is flip of that, which is cosine over sine. And secant is 1 over cosine of x, and cosecant is 1 over sine of x. In addition to these identities that we've already learned about, there are some additional identities that we need to know. So let's have a look at those. Like that. So this is, let me call it other useful trigonometric identities. Like that. So we say that, well, let's just write them out. There is no harm in duplicating what we've already learned. So let me write down some of them, not all of them again. So we knew that I'll first write these other ones, the previous one, in black ink. and then the new ones I will write in red ink, so they stand out as new identities. So these are the previous ones. Cosecant of theta is equal to 1 over sine theta, right? So cosecant is the reciprocal of the sine function. And secant of theta is the reciprocal of the cosine function. Cotangent of theta is the reciprocal of the tangent function. And we know that tangent of theta is equal to sine of theta divided by cosine of theta. And of course, the cotangent of theta is the flip of that, right? Tangent and cotangent are reciprocals of each other. So it'll be cosine of theta divided by sine of theta, like that. Okay, so in addition to these, here are 3 very useful additional trigonometric identities. I'm going to write down the most useful one and easy to use one. So sine squared theta plus cosine squared theta is equal to 1. Like that's the one of the very useful identities. The other one is the tangent squared theta plus 1 is equal to secant squared theta. And let's write down one more. So we have cotangent squared theta plus 1 equals cosecant squared theta. So there are more trigonometric identities coming up, and we every now and then we add a few more identities or formulas to the one we already know. So here are the 3 new ones. Okay, so let's use these in an example. So we want to write, in this example, we want to write the first trigonometric function in terms of the second function in the given quadrant. Okay, so here's let's see how many examples do we have. We have just one. So what they're talking about first in terms of the second, it is cotangent of theta, which is the first one, in terms of sine of theta, where theta, we are told, is in quadrant 2. Okay, that's what we want. So since we are already told to find cotangent of theta in terms of sine theta, where theta is in the second quadrant, I want to bring this back so we can look at it. In the second quadrant, which is that, right, this here, right there, the cotangent is it positive or negative? It's negative, right? And the reason for that is pretty clear, because cotangent is the adjacent divided by the opposite, right? That's cotangent. Adjacent divided by the opposite. So adjacent is positive. That's the positive y-axis. But opposite, that along the x-axis, that's negative, on the negative side of the x-axis, right? So adjacent, so positive divided by something negative, it'll be negative, which is that. Okay? So I just wanted us to get a feel for what is the algebraic sign of the cotangent before we actually went about and answered this question. Okay, so let's see, if we want to write cotangent in terms of sign, let's see if there is any of these properties that can help us. Well, first of all, can I use this? Can I use this one? If I want to write cotangent in terms of sine, can I use this formula? Think about it. Can you? No, we can't. Why? There is cotangent, there is sine. But there is cosine as well. We don't want cosine. We are asked to write cotangent in terms of only sine, not cosine. So that's why we are not able to use that one. Well, you look at the other ones, there is no cotangent anywhere. Well, how about this one? One of the three new identities we learned about, the cotangent squared theta plus 1 equals cosecant squared theta, has cotangent in it. But where is the sine? Well, the sine is actually part of the cosecant one, because we know that cosecant is the reciprocal of the sine function, and only sine function. So that's great. That's what we want. So let's use this formula to help us here. So we're going to write down cotangent squared theta plus 1 is equal to cosecant squared theta. All right? We're going to begin with that. Then we're going to substitute. So, well, or eventually we're going to substitute. But let's solve this for cotangent first. So we have cotangent squared theta is equal to, we're doing algebra now, right? Cosecant squared theta minus 1, moving this to the other side. But we want cotangent theta, so we need to take the square root of both sides, right? So square root of, square root of cotangent squared theta equals square root of cosecant squared theta minus 1, right? So is this correct? I've left out something. I'm not sure if you're going to catch it or not watching this at home, but I've left out something. What is it? Because this isn't correct. There's something missing. Do you remember what it is? Well, there should be, when we take the square root of both sides, one of the sides, right, for a square, taking the square root of squared terms, not cubic terms, not terms that are to the fifth power, but taking the square root of something that is to the second power really generates this by square root property. So I'm going to recall, and this is something that you must have seen either in Math 95-96 or Math 124 or even Math 126. So some of the earlier classes. So this is, let me say, by square root property, we must have plus or minus. Okay, so now we can continue with this and say that power and the index, which is 2 for a square root, cancel each other out. We end up with cotangent of theta equals which one of these? It can't be both, right? Which one of these is the correct one? We know that by square root property we should have both, plus or minus that, but which one is the one we want? Well, if you said minus, you are absolutely correct, because a couple of minutes earlier we decided that in the second quadrant, which is what this is, the cotangent is negative. So we cannot accept the positive answer. So we have minus square root of cosecant squared theta minus 1. Are we done? What do you think? Are we done? We're not done, right? We're not done because the problem asks us to write cotangent in terms of sine function, not cosecant function. So but we can easily substitute, right? We can come up here and say that cotangent of theta is equal to minus square root of 1 over sine of theta squared. Squared minus 1. Right? Because cosecant, you know that, right? We had it right here. We have it on this page. Cosecant of theta is equal to 1 over sine theta. So let's substitute for cosecant theta here with 1 over sine theta squared. So now we have, we can then, let's simplify this answer. So for the final answer, we have cotangent of theta is equal to minus square root of 1 over sine square root of theta minus 1, like that. Okay. Can we remove this outside? Can we say, oh, square root of sine of square root of theta is just 1 over sine theta? Can we do that? No, we cannot. Why? Because this isn't the only term under the radical expression. We have minus 1. What would we do with this? So we can't separate this, bring this out in front, and leave that in there. So this is the final answer. Okay. So let us do another example. Suppose we want to find So find the values of the related trigonometric functions of theta from the information given. So let's see what is the information given. We are told, this is the given information, that cosine of theta is equal to minus 7 over 12. And we are told that theta is in quadrant 3. Okay, so the blue, whatever you see in blue is given to us. And we need to find the values of the related trigonometric functions. That means the sine, the tangent, cotangent, and all of that. So given this, they want us to that means what they mean by that is what is the sine of theta? What is the tangent of theta? Cotangent of theta, right? These are related to this angle, or to this information. And the secant of theta, and of course the cosecant of theta. These are the values we need to find. Well, let's draw a picture. Let's draw a picture for what we have here, right? just to get a better feel for, because trigonometry is a very, very visual subject, and always a graph can simplify things. So I will draw that here. So x, and then y. Okay, so we have it's in theta is in quadrant 3. So, or in this case, so that would be right here. So I'll just draw an angle right here. That's theta, right? And the other thing we are told, like that, and is that cosine of theta is equal to minus 7 over 12. Well, we just learned about the relationship between trigonometric functions and the right triangle. So let's see if we can take advantage of that. So I'm going to just use the terminal side of this angle and draw and incorporate that as part of a right triangle. So like that. Okay. Like that. Like this. Okay, so if cosine of theta is equal to minus 7 over 12, does this make sense? Let's see. Well, cosine of theta, I'm going to write this down. Cosine of theta is equal to the adjacent over the hypotenuse. So this is why we cannot avoid memorizing this stuff. But hopefully, as you go through all these examples with me, you begin to remember these identities more quickly as we go through the semester. So that's the cosine of theta, which is equal to minus 7 over 12, right? Well, that means that this is 7, or it should be minus 7. That's where the adjacent over the hypotenuse. So yes, so minus 7, we can look at that. And then hypotenuse is this one, the terminal side, 12. Right? Let's see. So I want to know. I want to, guys, I want to change this. So we're in the third quadrant. So this is 7. That distance is 7. Distance 7. And then, but because we are in the third quadrant, we are told we're in third quadrant, which is that quadrant, this quadrant. So naturally, then the cosine of theta is going to be, let's see, a negative x value divided by that. So this sine, this minus 7 over 12, is compatible with which quadrant the angle is. So that automatically the negative comes in because we know that that's connected with which quadrant we're in. So in that quadrant, let me bring this back, cosine is negative. So we're in third quadrant. So cosine of x in this quadrant is negative. So that's where this negative comes from. So we can just put the positive 7 as the length of the adjacent side over the hypotenuse. Okay, so now knowing that, then what about sine of theta? Well, sine of theta is the opposite side divided by hypotenuse, but we don't have the opposite side. But that's no problem because by Pythagorean theorem, we can calculate the missing side, the length of the opposite side. So let's do that. So we have by the Pythagorean theorem. What do we have? We have we have 12 squared, or let's call this, what do we want to call it? I'll call it opposite. So we call it 7 squared plus the length of the opposite side squared, that's the opposite squared, will be equal to what value? Do you remember the Pythagorean theorem? So 12 squared. Okay, so we solve this for opposite. What do we get? We get 49 plus opposite squared equals 144, and then we have opposite squared, that's the opposite length, equals to 144 minus 49. Was it squared equals 95, and so the opposite, we have to take the square root, right? Square root of opposite squared equals plus or minus square root of 95. Once again, I'll remind you, this is by the square root property. Like that. Okay, so but which one? Right? Which one of these is the correct? The opposite side is in the third quadrant where the y values are negative, right? This is a y value, so in the third quadrant, so it is negative. So therefore, we have the opposite side is equal to minus square root of negative 95 in quadrant 3, right? Like that. Okay, so now that we have all these three sides figured out, this being negative square root of 95, let's put them all together in the calculation of these angles. So we have sine of theta. We need to figure that out, right? Sine of theta is equal to the opposite divided by the hypotenuse. So that would be minus square root of 95 divided by 12. So that's the sine value. The tangent is next. Tangent theta would be opposite divided by adjacent. So we have adjacent divided by the adjacent or opposite. So the tangent is opposite divided by adjacent. But the opposite is in which quadrant? In the third quadrant, the y values are negative. And the x values, which is where the adjacent is in the second quadrant, where x values are negative. So negative divided by negative is going to be positive. All right, so this is opposite divided by adjacent. So this is, everything is going to be positive, and this is, what do we have? We have, opposite was negative, or it's going to be positive, so negative square root of negative 5. We can get to it that way too. Minus 7. So because this is once again, the adjacent is along the negative x-axis, and we might as well put that here. It makes no difference though. We can put that as negative 7 if you want, but this has no relation with the sign of this number, but this is in the second quadrant. That's why this would be negative when we plug it into the formula here. And then we have as positive square root of 95 over 7, like that. And cotangent of theta, cotangent, it is the adjacent divided by the opposite. Of course, that's adjacent is along the negative x-axis. The opposite is along the negative y-axis. So negative divided by negative is positive. So what we would expect to see looking at this drawing, right? The cotangent and tangent in the third quadrant are positives. Okay? So this would be just the reverse of that. Once we know the tangent, we know the cotangent. It's just the reciprocal of that. So 7 over square root of negative 5. And then I'm going to try to fit the rest of this here on the same page. So I'm going to write the secant of theta, which is 1, which is equal to 1 over, do you remember which one? Which trigonometric function? Secant and cosine functions are reciprocals of each other. So 1 over cosine of theta. And cosine of theta, we already know it is negative 7 over 12, right? We know that was the information given to us from the outset. So take the reciprocal of that, and we have minus 12 over 7. So, and the secant function in the third quadrant, secant function is negative. We would expect that because it's the reciprocal of the cosine function. So 1 over any negative number, it's going to be a negative number. Okay, finally the last one, the cosecant function, or cosecant of theta, is equal to, do you remember what trigonometric function is the reciprocal of this? Remember that? That's the sine function, right? So 1 over sine of theta. So that means it's the reciprocal of the sine theta. For the sine of theta, we got minus square root of 95 over 12. So just take the reciprocal of that. We have minus 12 over square root of 95. Like that. Okay. So I'm sure if you have questions about what we did just now, you'll let me know. Okay, so having talked about this, let's continue our discussion with a little more in this section about the area of a triangle. So from the basic high school geometry that we know, the area of a triangle, of a right triangle, is equal to 1/2 times base times the height, right? Once again, the area of a triangle, of any triangle, not just the right triangle, the area of any triangle is equal to 1/2 times the base times the height. Okay, so let us, but we're going to connect that formula, which comes to us from elementary geometry, connected to trigonometric functions, right? We're going to do that. Okay, suppose we have a triangle like this. And suppose we know that this is theta, and this side is b, and this height is h. H, like that. And let's say this side we are told that is equal to a, this whole base. So either this triangle, or let's look at, so let's see, AB sine of theta. Okay, so that, and I want to draw okay, so let's draw another triangle on this side. Oops, I went too far. So I want to make this line here dashed. So I'm going to try to, it should have been dashed. So that, like that, like that, like that, like that. Okay, and then we have we have this side with an obtuse angle like that. Like this. And let's connect these. These two lines. So we're doing that. Okay, and then of course the height of this this triangle is this vertical line, like that. And so this is at 90 degrees, and this is the height h. And let's say that this side is, the length of this side is b, the length of this side is a, and and this is theta. And so theta right here. Okay. So we want to say, let's see. So here theta is acute. So let me add to this. For this triangle, theta is acute, meaning less than 90 degrees. And here, where theta is not acute. So these are two different cases, right? Theta here is not acute. It's larger than 90 degrees. Here, it's less than 90 degrees. Okay, so those are the conditions. Then we know that, so according to this side, according to this, then we have sine of theta, right, is equal to the opposite divided by the hypotenuse. So it'll be equals h over b. And then from this relationship, from this triangle, we have h equals b sine of theta. Right? Okay. So now, instead of, so here though, we remembered from the reference angles, right? Remember the reference angles? So this sine of this theta is equal to let's see, would be equal to the sine of the reference angle here, like that. The terminal side, the angle between the terminal side and the x-axis here. So we already know from the elementary algebra, or elementary geometry. So from elementary geometry, we know that area of any triangle is half times the base times the half times a times the height. That, according to this graph, right? That's from elementary algebra. So now, instead of instead of h, replace h according to this trigonometric relationship between the height and the trigonometric sine of theta, between sine of theta and the height. So let's replace that. So replacing h with b sine of theta, we have this new formula that has the sine of theta involved. So we have the a equals 1/2 a b sine of theta. So that's from here, after we substitute b sine of theta for h. Okay, so let's use this in an example. Let me just 1 second. So I wanted to test out something. So if we have, so let's say sine of 150 degrees, sine of, and sine of 30 degrees. Okay, yeah. So this, over here, this second figure, this formula is applicable to this second figure as well, even though the theta is not acute, because the reference angle, suppose if you have, say, if this is 120 degrees and this is the reference angle is 60 degrees, so sine of 120 and sine of 60 degrees, it would be the same. So that's why whether theta is acute or theta is larger than 90 degrees or not acute or obtuse, I guess, if theta is obtuse, which is larger than 90 degrees, then this formula still applies, because theta in either case, it would be either the reference angle, either the reference angle or the actual angle. So either way, it would be fine. And so let's that. So suppose, let's do an example of this, applying this formula. So find with side of length 10. Right? Okay, so as before, let's draw a picture. This is not a complicated problem. We probably don't need a picture for this problem, but let's draw one anyway. because it makes it more understandable as to what we're doing. So here, this is an equilateral triangle. I'll try to do my best to do that. So we have a triangle like this, and then let me draw a side from here to here, maybe a little bit higher to make it more equal to this side and that side, maybe a little bit higher this way, that's better, and then that like that. So I'm sure I'm off, but let's assume this is an equilateral triangle. So for equilateral triangles, we know that the angles should be equal. So this is 60 degrees, 60 degrees, and 60 degrees, right? And find the area of an equilateral triangle with side of length 10. So this is 10, this is 10, and this is 10. Okay, so applying this formula, we have A equals 1/2 times A would be 10, B would be 10, times sine of 60 degrees, right? Okay, so this would be A is equal to 50 times 0.8660254, and A is equal to 43.30. So whatever the units, right? So if this was meter, this would be, if this was meter, this would be meter squared. If this was feet, this would be feet squared, and so on. Okay, thank you for staying with me until this section. We finished discussion of section 6.3. And so when we come back next time, we will begin with section, I believe next one is 6.4. So thank you again for joining me, and have a nice day, and I'll see you next time.